Well, here is a shorter discussion that wouldn't fit well in class time to help you know a little bit more about the simple monosaccharides that are common and helpful to know more about. Glucose is the most common sugar in the blood and in all kinds of other polysaccharides and disaccharides, etc. It is also known as grape sugar. It is an aldohexose, not obvious from this particular representation. It has a name that's called dextrose that you'll sometimes see in food labeling, but it got that name because of its positive or clockwise optical rotation. No big deal, but that's where the name comes from. Glucose occurs in three forms in solution, and the majority of these are the cyclic forms. 36% is the alpha D-glucose and 64% is beta D-glucose. A very small amount is in the open chain form. All three forms are in equilibrium with one another, but primarily they're in the closed forms, and the beta D-glucose is the most common form. Happens to be the most stable. How does it get from one form to the other? It's this thing called mutarotation. It's what happens in the resulting change in optical rotation in a molecule that has to do with the ring opening and closing. But when the ring opens, the bond around the carbonyl of carbon 1 has to rotate, and it is shown in this diagram between model 2B and model 2C. We talk about this in activity 10. And if this bond between carbon 1 and carbon 2 can rotate, then this position of the carbonyl is not necessarily up, but down. And so in model C, the position of the carbonyl is pointing downward, which gives you a different orientation of the resulting OH group when the ring closing hemiacetal formation occurs. So you can go between the form that's pointing with the OH group on the left, or on the top, on the left diagram of A, to the one that's down on the right. And these are given different designations, beta and alpha. And this idea of mutarotation means that whenever you have the hemiacetal present, the hemiacetal carbonyl marked with a quick little S or little star, that hemiacetal carbon being present means it's going to be in equilibrium with two open chain forms, or the open chain forms with either the carbonyl pointing up or down. And if it rotates again, you'll get a different orientation as the ring closes. So it's a change in the optical rotation, and that's why it's called mutarotation. All of the monosaccharides that occur naturally in solution are typically found in the closed ring form, but it can be either alpha or beta because of mutarotation. All right, so with glucose, as I said, most of it is the beta form and very, very little in the alpha form. Remember that alpha and beta designation is based on the orientation of the OH group, the alcohol hydroxyl group, on carbon number 1, the anomeric, aka hemiacetal, same thing, carbon atom, the one that was previously a carbonyl. And alpha has the OH group pointing down relative to carbon 6 pointing up for any D sugars. And the beta orientation has the carbon 1 OH group pointing up when carbon 6 is pointing up, which it will be for any of the D sugars. So beta and alpha differ at only that one spot, carbon 1, the anomeric carbon. Now, note the pattern for beta D-glucose. Beta D-glucose is the one that's very prevalent, so it's a really good one to notice, and it's one to which the others can be compared, and it makes them easier to recognize. With glucose, the pattern can be described as follows. If you start with carbon 6, whoops, sorry about that. If you start with carbon 6, the pattern is up, down, down, and up if you look at the OH groups on each of the carbons around the ring. So carbon 6 is pointing up, Carbon 5 no longer has an OH group. Whoops, backwards. I meant to say that differently, didn't I? So this should be carbon 4. Whoops. 4, because carbon 5 no longer has an OH group. Carbon 3 is going to be up right here, and 4 was down, and then carbon 2 is down, and carbon 1 is up. Let me fix those numbers. Sorry about that. I just got counting along here and wasn't doing it correctly. So carbon 1 being up, the OH group going up, all of the OH groups present in beta-D glucose will be alternating, starting with carbon 6 being up. And when carbon 6 is up, that means that the sugar is a D sugar. We'll see more about that in activity 10. That's always the same for D sugars. Okay, other things to know about the monosaccharides. So the remaining things to know about monosaccharides have to do with a few little tidbits about their actual physical state, including the fact that they are white crystalline solids, just like in your sugar bowl, and that's because they're high melting point compounds with all those hydroxyl groups that makes them very high melting point compounds. You can also see more about this in your text. Notice that either the alpha or the beta anomer of glucose is still a D glucose, and they have the same optical rotation in a clockwise sense, but differing magnitudes. Not a big deal because you're not going to actually look at the details on those. So here's a couple of funny cartoonish things that are t-shirt designs, honestly, and they're actually glucose. So if you take a look at these, you can figure them out. But it takes some getting used to because these cyclic forms are represented slightly different ways at times. The one on the top left has glucose in what is called the chair formation, and the hemiacetal oxygen is shown right there. And so that means that carbon 1 is to the right of it, carbon 2 follows next, carbon 3, carbon 4 thereafter, carbon 5 is the next one in the ring. If you stare at it, you can see that, I think. And carbon 6 is the one that's not in the ring. So if you remember what I just described for the pattern of the OH groups in glucose, does this one fit? So carbon 6 should be up. Carbon 4 is down. Of the two choices on that carbon, that's going to be down. Carbon 3 should be up, which of those two choices, that is the upward pointing one. Carbon 2 should alternate and go down. And carbon 1 is up. In those two choices, that is again up. So it's a relative orientation being up on each corner is how we're thinking about these things, relatively up or down. So this one is in fact beta-D glucose, just like the previous slide, but it's shown in what we call the chair conformation. Now, the other diagram on this slide, is it also probably glucose? It's pretty likely because it's such a common example. So if we start with carbon 6 going up, carbon 4 is the next one on the ring, goes down. The one on carbon 3 is going up, and the one on carbon 2 goes down. Oh, but this one has an OH in a different group, different position. Is that still glucose? Yes, but this is the alpha form of D-glucose instead. A little bit of silliness in t-shirt designs. So another carbohydrate, simple monosaccharide that is important to know because of its occurrence in a disaccharide is galactose. Galactose is known as brain sugar because of its association with the glycoproteins that we'll talk about later. Glyco means sugar, and glycoproteins found in brain and nerve tissues tend to include galactose. So it is also important because it's in your diet from milk products. It is 1/2 of the disaccharide lactose. So in order to recognize lactose, it helps to understand or recognize galactose. Notice the overlap in the names. The interesting thing is that it's terribly similar to glucose. If you recall the pattern from glucose, the galactose is just a little bit different. So take a look here. Instead of being alternating, starting with carbon 6 going up and than carbon 4 going down. Carbon 4 is the one that's different on galactose. Other than that, beta-galactose is going to be essentially the same as glucose. It is an epimer. That's a funny name, but don't panic. It's just a way of describing the fact that it's got a different orientation at carbon 4. And so if you flipped carbon 4's orientation of the OH group, that would in fact be galactose, or glucose. So it's metabolized that way, and they're very similar. But it makes a difference one way or the other in terms of digestibility and such, that galactose is unique from glucose. So the two forms of these two anomers of galactose are shown here, the alpha and the beta anomers of galactose. And if you have to answer where the anomeric carbon is, it is the one where alpha and beta is determined, namely carbon 1. In each case, it's the hemiacetal that is the anomeric carbon, the one that determines alpha and beta orientations. So beyond that, galactose is very similar to glucose. The next monosaccharide is fructose. Fructose is the oddest one of the bunch in some ways because it is a ketose, a ketohexofuranose. Furan refers to the fact that it's a 5-sided ring, and it has the greatest sweetness per gram, and that's why it's commonly used in food products, to fewer calories per amount of sweetness added by using fructose, but whatever the case, we all like fruit. It often has this other name called levulose because of its counterclockwise optical rotation, but that's not a critical aspect to know at this point. Here are two anomers of fructose, again the alpha and the beta anomers of fructose shown in their cyclic hemiacetals. The cyclic hemiacetal is interesting to figure out because the anomeric carbon is from a ketose, and so it would be the one which has a hemiacetal, in this case carbon number 2. I should put an asterisk instead. And it's the one that has the ether and the OH on the same carbon, and you'll get the alpha anomer when the OH is positioned in the downward orientation, and beta when it's pointed up. Fructose is quite similar to glucose in spite of its distinctly different shape, if you remember the similarity to the pattern with glucose. Glucose was alternating up and down if you started with carbon 6. Well, let's take a look at fructose and compare. I'll start on the left side here. The fructose has carbon 6 last group pointing up. Carbon 5 doesn't have an OH group. Carbon 4 is down, alternating again. Carbon 3 is going up. Now, from there, it's going to be up or down depending on alpha or beta, but as far as 6, 5, 4, and 3 are concerned, it's an alternating pattern just like glucose. It's because the bottom 4 carbons of fructose look the same as glucose in all their orientations. So it's very similar to glucose in that respect, but from carbon 2, which was the ketone, to carbon 1, which is the CH2OH group, there have to be some differences. Notice that a ketose will have this second CH2OH group. Whenever you have a ketose, there's 2 of those in your structure. Beta will have the OH pointing up in fructose and down on carbon 2. The anomeric carbon is alpha. All right, last of the simplest monosaccharides of interest are ribose and its first cousin, 2-deoxyribose. These are aldopentoses, and again, like fructose, it's a 5-sided ring, would be called a furanose, but I'm not going to test you on that name. This 5-sided ring is a little simpler than fructose because it doesn't have as much going on with only 5 carbons. And ribose is easy in the respect that carbon 2 and 3 are pointing in the downward orientation always, and the common form shown here of beta D ribose, remember that this last carbon being in the upward direction tells you it's a D sugar, is the way that ribose is going to occur in places like RNA, and its cousin deoxyribose in DNA, commonly in that beta orientation where the OH group on the anomeric carbon is pointed up. Some people call ribose like a camel. Use your imagination if you will, because this could be the head of the camel and the hump is here, it has 2 feet, and the tail is carbon 5. So laugh if you will, but maybe it'll help you remember what ribose looks like. Its cousin here, beta D2-deoxyribose, is exactly what it sounds like. 2-deoxy means that carbon 2 lacks the oxygen, the OH group, that the ribose otherwise has. So it's terribly similar, but again unique and important because of its occurrence in DNA. So if you can recognize ribose, deoxyribose is going to always be 2-deoxyribose, and it's very similar in that respect. Now, the question's at the bottom of the screen. Are these two compounds anomers? And if you recall where the anomeric carbon is, it's the one with the hemiacetal. Anomers are a pair of compounds which are the same other than the orientation at that hemiacetal carbon. In this case, the answer would be no, because deoxyribose is not even an isomer. It's lacking in oxygen. And I answered the second question then. The number of the anomeric carbon on each is carbon 1, which is a common pattern. All right, I hope that this is a way to help you recognize and be familiar with these basic monosaccharides that will be used when you have to understand disaccharides and polysaccharides later. Good luck with your studying. See you in class.